Okay, I'm gonna go ahead and get started with this week's Sunday review. So today we're gonna be talking about machine level code. So this is mostly assembly we're gonna be talking about, also gonna touch a little on C and machine code. So I'm gonna go into assembly basics, how registers work in assembly, how you can move the data around, different arithmetic computation as well as address computation. And then I'm going to talk a little bit about conditional flags, conditional branches, and what those bits are to set. So first off, we have just the super basics of machine level coding. So the ISA is the instruction set architecture, and it's the parts of a processor design like x86 or ARM, which is used in phones, i32, etc. ISA you will be talking about a lot more coming up this semester. So that's going to be things like you have your PC register and it's connected to like um oh gosh, I'd have to look at diagram to know what it's actually connected to, but it's going to be connected to things like your memory and your operators, and like that's your ISA. PC is your program counter, so that's going to hold the address of your next instruction. So in x86-64, it's going to be the RIP register that holds that register file. The program data that gets used / referenced often, so that's going to be, I've showed you all the chart before that has a bunch of boxes. That's your register file, and it's going to hold data that you're going to use continuously in your code. So condition codes are things that store status information about the most recent operation. It's also used for branching. Those can be implicitly and explicitly set. I'm going to talk about that at the end. Machine code is a byte level representation of your code. So if we're going in order, C, assembly, machine, unreadable, that gets processed. So machine is like the lowest level that we can read. Is it easy to read? No, because it's binary, but you can still read it. And then assembly is the text, supposed to say representation of machine code, which is what we're going to be looking at a lot and what you're going to learn how to write in. So you can compile C into assembly by using this here, this GCC -OG-S, and then the name of your file in C. Let me fix this real quick. Anyway, so yeah. So in assembly, these are the data types that you are able to work with. So you can work with 1, 2, 4, or 8 byte ints. Floating point numbers that will be 4, 8, or 10 bytes. Code, which is byte sequences that are encoded, that encode series of instructions to use. If you want to use arrays, structs, etc. in assembly, they don't exist. They aren't real. So if you write C code and you have a struct in there and then you convert that to assembly, what assembly is going to do is have the bytes in memory of that like list, those chunks are going to be allocated next to each other, which goes along with the RAM model of computing, random access memory. So when they are next to each other, they're easier to access, which is why it puts them all together. Okay. So next up, we're going to talk about how you can move data in assembly. So there are 3 sources that you can use for the move queue destination, move queue instruction. So move queue looks like this. It's just move queue and the source and the destination. The immediate operand is going to be this first chunk here, which is the source being constant integer data. So what that means is quite literally, you have a little $sign in front of constant int data. So you can see how it relates in C. So register operands are you getting the source from one of the registers, so something that is already exists in a storage place. So it's going to be this here. So you can see from you're moving RAX into RDX. So temp 2 would be where our RDX is, and temp 1 would be RAX. And then we have memory operands, which are the source. Your source is 8 bytes of memory at an address. So you can see with this bottom one, these parentheses are meaning it's an address. That's how you get our pointers and our dereferences. So if you want to do a memory to memory transfer, meaning you want to do RX and then maybe you want to put parentheses on this RDX, you can't do that with one instruction. It won't work. It'll error. So you'd have to do multiple. Okay. So these are the registers in x86-64. They all have semi-specific purposes. Most of them are general use. You can use them for anything except for the RIP register, which I talked about earlier, but a lot of them have things that default you should be using them for. So like RAX, if you're gonna return a value, you're gonna want to put that in RAX. The first argument is RDI, and then you fill up, callee saved. Gonna talk about callee caller a little later in the semester, but you have your RSP, which is your stack pointer. Super easy to remember because it's literally SP, stack pointer. They help you out a little. And then a bunch of other registers that you don't really use that often in this course. So these are the different address modes when you are addressing things to be used in commands. So as I said earlier, if you put parentheses around a register, it gives you that memory address, which is the same as pointer dereferencing. If you put a number in front of a parenthesis or in front of a register, that's going to offset that memory address by that number. So it's basically adding to it. When I say offset, I mean offsetting right, adding, not offsetting left, subtracting. If you want to scale something by a factor of 1, 2, 4, 8, those are the only factors you should be scaling things by address-wise, because otherwise you're going to be scaling to the middle of an address. Because if you remember when I talked about all of your stuff is in these increments, like your addresses are going to be stored like, you could have an integer in the first 2 and then a float in the next 4. So it's 2, 4, 6 total. If you scale by 5, if you scale your 1 by 5, you're going to end up 5. You're going to end up in the middle of something, and that doesn't work. So only use those numbers to scale. But as you can see, there's an example of scaling here. It has the source, the destination, and then the scale. Destination, source, scale. Cool. So address computation and arithmetic computation. So address computation is going to be with this LEAK. I personally, in my head, say leak. The professor could say leak. It feels like a leak. Like I call it leak. So that's what I'm gonna be calling it. So this leak here is going to let you find the address to things. So the source, the first one is going to be the address mode expression. So that's going to be one of these type things. And then the destination is going to be the address where you're going to be saving that. So if your leak is here is RDI, RDI2. So that's going to be RDI plus RDI times 2. And you're going to be saving it in RAX. So you're going to be getting that address here, saving it here. So this is just kind of a expanded version showing what that means. And then we have a bunch of other arithmetic computations. So the ones that get used a lot, you're going to be using addq a lot, subq, not imulq as much because there are a lot of systems and management that imulq just won't work. So if you want to multiply by something, I highly recommend using leak and scaling. Could be using these logical XOR and Q, the OR Q a lot. Increment, decrement, negative, not. They're all super helpful, and it's just sort of set up all of them are except for these last four, which are the increments, and they don't have sources, but all of them are set up source dest, where it's the dest will be equal to the dest whatever source. So it's really, you can think of it kind of as like specifically for add dest plus equals source. Same thing for the minus, same thing for the, like, that's an easier way to think of it. If that's an easier way to think of it, that's the same thing. Cool. So as I said, these are the ones you're going to be using most often. There are tons more. You can find them in your textbook, but these, especially these two, or these three at the top, and these will be their most helpful. These will be your most helpful. So next I'm going to talk a little bit about conditionals. So these are all single bit flags that can be either implicitly or explicitly set while you're doing things in assembly. So first I'm going to talk about the definitions and how they are implicitly set. So CF is going to be your carry flag. As I said, it is 1 bit denoted by either 0 or 1. Carry flag is for unsigned ints. So when you're working not in 2's complement, it gets set if the carryout from the most significant bit exists. So if there's overflow from the last arithmetic operation. So these are set implicitly on the last arithmetic operation. So if you do 2 adds and the first one sets the carry flag and the second one doesn't have a carry, that carry flag after both of those statements is going to be 0 because it's from the last operation. Then we have the 0 flag, also 1 bit, is going to be set if the number equals to 0 from an arithmetic operation. Sign flag, also 1 bit, will be set for signed integers. So if it's less than 0 is assigned. If it's a negative number, that one's going to be set, and that's going to be with 2's complement. And then we have the overflow flag for signed, which is going to be set if 2's complement overflows, aka if it needs a carry from 2's complement. So none of these are set. I need to start proofreading these. This is so bad. I'm so sorry. None of these are set by leak. These are all set by the last arithmetic operation. Now, you can explicitly set flags if you want to make sure that something is being set. So if you use this compare instruction, so it's going to be compq source 2, source 1, it's basically the same as computing a minus b, except for you're not saving that anywhere. You're just finding out what that comparison is. So if a minus b is less than 0, it's going to set your sign flag. If a minus b is equal to 0, aka a and b are equal to each other, then it's going to set that 0 flag. You can also explicitly set flags from using the test instruction, which is test q source 2 source 1. And that is basically like computing a and b. So the 0 flag gets set if a and b is equal to 0, equals 0, which means they're not equal to each other. The sign flag is set if a and b is less than 0, etc. So here's a bunch of conditions that you can set with these setx instructions. You're not going to be using those a whole lot. Still super cool to know, super good to know. Especially these condition to descriptions, are really good practice for understanding how the flags work. Okay, next up with the conditionals, we have JX instructions, which are jump X. Or to me, they're just jump. Like I just think jump, different types of jumps. And that's how you jump to different parts of the code depending on the condition codes that are currently set. So you can go through the JX instructions. This first one is just jump. You'll always jump no matter what. So that's if you like set a separate area in your code, like somewhere else, like down the line, and you're like, hey, jump to loop, jump to subtraction, like it's like dot and then you name it, and it's gonna be like a separate section. That jump will always go there no matter what. So JE, on the other hand, will only complete that jump if the zero flag is set at 0, or the numbers are equal, which is set at 0. JNE is only gonna jump when the 0 flag is not set. JS will only jump when the sign flag is set. JNS, when it's not set. JG is when there's a greater number of these flags, etc. And those are going to help you a lot. If you have like an if statement, and if you want to do this, then, so say if A and B are equal to each other, you want to add them together. But if they're not, you want to subtract them. What do? You have a JE. If they're equal, 0, then you'll jump to that part that does that add. Otherwise, J and E, they're not equal, you'll jump to a part that does that subtract. You're basically just telling the code the conditions that you have to meet to do something else, rather than it kind of being implicitly in there with your conditional statements. Okay, and then that is everything I had specifically prepared for today's session. Next time, my plan is to go over goto, loops, switch statements, the stack, and then call returns. I can take questions now.